Here we are in Chapter 7, Section 5, which is about using the Pythagorean Theorem. So, in what other ways can we use the Pythagorean Theorem? Well, we're going to introduce some new vocabulary here. We have the converse. Let me get my color. The converse of a statement switches the hypothesis and the conclusion. So let's say we have a statement, if P, then Q. That's the original statement. Well, the converse of that statement is just if Q, then P. So all it does is switch the hypothesis with the conclusion. So this should be written in your notes, okay? So let's look at this example. If A equals B, then A squared equals B squared. So if P, so A equals B is my P, then Q. So A squared equals B squared is my Q. So the converse is if Q, then P. So that's if A squared equals B squared, right? Because I'm just putting in Q there. Then A equals B. Then P, right? That's my P value. A equals B. Well, this is the converse, right? This here is the converse of this statement here. However, now we can analyze the converse and say, if A squared equals B squared, then A equals B. Is that true? Well, let's put in different values for A and B here. Let's say if 2 squared equals negative 2 squared, so A equals 2 and B equals negative 2. Those are equal, right? This comes out to be 4 equals 4. Positive 4 equals positive 4. Well, so then does A equal B? Does 2 equal negative 2? No, it does not. So the converse is not always true. So let's just say that one more time. This statement here is the converse. But even though it is the converse, after we write it, we then decide, well, is it true or is it false? And in this case, it's false. Let's look at another example. Okay, so here we have if two triangles are similar, then the triangles have the same angle measures. So we have if the two triangles are similar, that's if P, then the triangles have the same angle measures. There's Q. So my original is if P, then Q. So my converse is if Q, then P. So if the triangles have the same angle measures, then the two triangles are similar. Is this statement true? Yes, it is true. So we would write true, because if two triangles have the same angle measures, then they are similar, right? If their corresponding angles are the same, they're automatically similar. We know that. So in this case, the converse is true. So you can see from these just two simple examples that the converse of a true statement is not always true. It can be true or false, right? So in this example, if two triangles are similar, then the triangles have the same angle measures. That's true, right? That's a true statement. The converse is also true. In our previous example, that wasn't the case. The converse was false, even though the original statement was true. So what does this have to do with the Pythagorean theorem, you're asking? Well, let's look at the Pythagorean theorem in terms of an original statement and a converse. If we say A squared plus B squared equals C squared, that's like writing if A squared plus B squared equals C squared for the side lengths of a triangle, then the triangle is a what kind of triangle? A right triangle. Very good. So my statement, if P, then Q. If A squared plus B squared equals C squared for the side lengths of a triangle, that's my P, then the triangle is a right triangle. That's my Q. So the converse is if Q, then P. So the converse would be if the triangle is a right triangle, then A squared plus B squared equals C squared for the side lengths of a triangle. Is that converse true? Yes, that is always true, right? If it's a right triangle, then the Pythagorean theorem is always going to work. Likewise, if the Pythagorean theorem works, then it's a right triangle. So that being said, if we were given the three side lengths of a triangle and we wanted to figure out whether or not it was a right triangle or not, we just plug the side length values into A, B, and C in the Pythagorean theorem. And if the equation rings true, then yes, it's a right triangle. If it does not ring true, then it's not a right triangle. So let's look at an example. So here we have this right triangle, and we will label this A, B, and the hypotenuse is C. So we want to know if this is a right triangle or not, and we want to prove that. So we have A squared plus B squared equals C squared. So 9 squared plus 40 squared equals 41 squared. 9 squared is 81. 40 squared is 1,600. And 41 squared is 1,681. So 81 plus 1,600, that's 1,681, equals 1,681. So yes, this is a right triangle because when you substitute the side lengths into the Pythagorean theorem, the equation is true. Let's look at another example. So we want to know, again, is this a right triangle or not, and we want you to prove it. So let's go ahead and label our sides. The shortest we'll do A, B, and the hypotenuse is C. So we have A squared plus B squared equals C squared. 12 squared plus 18 squared equals 24 squared. 12 squared is 144 plus 18 squared is 324. 24 plus 24 squared, which is 576. 144 plus 324 equals 468. And that does not equal 576. So no, this is not a right triangle, and this is your explanation right there. So now you're going to try a few. Tell whether the triangle with the given side lengths is a right triangle. So instead of drawing a picture in this one, it has just listed the side lengths for you. So you plug those in to A squared plus B squared equals C squared and see if you can figure out whether or not these side lengths make up a right triangle. Let's say we were given a triangle on a grid or on a coordinate plane. And instead of being given the side lengths like we were in the previous examples, we had to find the side lengths and then use the converse of the Pythagorean theorem to figure out if the triangle was a right triangle. So in order to find the side lengths, given the points of the vertices, we need another formula. So we're going to use the distance formula. So this definitely needs to be recorded in your notes. The distance formula is d equals the square root of x2 minus x1 squared plus the quantity y squared minus y1 squared. So just looking at this example here, we can be given three vertices, right? We have x1, y1, x2, y2, x2, y1. And then we find the distance between these points, except it looks a little bit different. You don't have to find actually the distance between every single one, because if you make this, like if you plug it in like this, y2 minus y1, and this x2 minus x1, for your A and B, that's going to give you this D. So let's look at some examples. So you should have this formula recorded and have it labeled the distance formula, and then you need to copy this in your notes, okay? This whole diagram. So first, let's look at an example, just a simple example using the distance formula. If I want you to find the distance between 1, 5 and -4, -2. So we'll say this is x1, y1, and this will be x2, y2. Okay, so we're going to use the distance formula. D equals the square root of x2 minus x1 quantity squared plus quantity y squared minus y1 squared. y2 minus y1. Sorry, this is y2 and this is x2, not x squared. So now we're just going to substitute in our values. So D equals the square root so x2 minus x1. So I have my x1 is 1, right? And my y1 is 5. And my x2 is -4, right? That's a -4. And my y2 is -2. So now I get D equals the square root. -4 minus 1 is -5 squared, so that's 25, right? Plus -2 minus 5, that's -7. -7 squared is 49. So I get D equals the square root of 74. And that is not a perfect square, so you can just leave it as that. D equals the square root of 74, and you're done. So that would be an irrational number, right? Okay. So that's how you use the distance formula, right? So now let's look at an example with a triangle on a coordinate grid. So let's look at this word problem. You design a football play in which a player runs down the field, makes a 90-degree turn, and runs to the corner of the end zone. Your friend runs the play as shown here. Did your friend make a 90-degree turn? Each unit of the grid represents 10 feet. So here we see the starting position. So your friend runs here, makes the turn, and then runs there, or about there. Okay, so we want to figure out, is this a 90-degree angle? That's the question. In other words, does this triangle satisfy the Pythagorean theorem? So, step 1, you use the distance formula to find the lengths of the three sides. And here you get the three side lengths, right? So that's step 1, use the distance formula to find the lengths of the three sides. So this is a bit time consuming, right? Because we have 3 xy points there. And so you have to do the distance formula 3 times to get distance 1, distance 2, and distance 3. So use the converse of the Pythagorean theorem to determine if the side lengths form a right triangle. So you just plug in your A, B, and C, A, B, C, and see if it's true. And 1,800 plus 5,000, that does equal 6,800. So yes, it checks out. Your friend does make a 90-degree turn because these side lengths all satisfy the Pythagorean theorem, then you know it's a right triangle. Okay, and this is your only practice problem because you're in class, so you're about to practice from the book. So I won't give you additional practice problems to do, but I want you to figure this out with your partner or the people around you. Which one doesn't belong? So which set of numbers does not belong with the other 3, and explain your reasoning. So you'll have a few minutes and then share with the groups around you and then get started on the practice.